Section 4.6, Operations with Complex Numbers. Now, there's really only one problem that I'm going to be doing in this whole section of notes that is going to directly relate to our work in this chapter with solving quadratics, and that's basically using what we did yesterday, and if we end up with it equaling, our x squared equaling a negative number, then that's where complex numbers is going to come in. The rest of this section and most of your exercises are simply dealing with the properties of complex numbers in the imaginary unit. Since this is your introduction to that imaginary unit, it's just kind of to expose you to the properties of that imaginary unit. So the imaginary unit I, a complex number has a real part and an imaginary part. And the standard form of a complex number is a plus bi. And a and b are real numbers. And when you first were introduced in Chapter 1 to all the numbers, there were real numbers and there were imaginary numbers. And so this now we are going to be exposing you to imaginary numbers. And so what's important is the definition of I is actually the definition of the square root of -1. As you know, the reason that the square root of 25 is 5 or -5 is because 5 times 5 times itself is 25, and -5 times itself is also a positive 25. So you can't multiply two numbers together to get a negative number because one of them has to be positive and one has to be negative. And so we have I. And so then this extends to I squared, because sometimes when you're dealing with I, you're going to have to square it. And keeping in mind that I squared is I times I, this is the square root of -1 times the square root of -1, which is the square root of -1 squared. The squaring and the square root undo each other, and so we're left with I squared equals -1. I to the third is I times I times I. Well, we could regroup this as I squared times I. I squared is -1. And it's times I, so we get -1, or sorry, I cubed equals -I, so it's the same thing. I to the fourth, again, we can rewrite this as I times I times I times I. If we group these as I squared times I squared, we have -1 times -1, so anytime we come across an I to the fourth, that's actually the same as 1. And so we can extend this, and anytime you have I raised to some power, that's going to be the same as either I, -1, -I, or 1. So for example, I to the 10th is the same as I to the 4th times I to the 4th times I squared. And we want to use I to the 4th because I to the 4th is 1. So when we rewrite these with their equivalents from the previous page, we get that I to the 10th is the same as -1. If we look at I to the 7th, that's the same as I to the 4th times I to the 3rd. So 1 times -I is -I. So I to the 7th is the same as -I. And you can do this to any power of I. And so now some examples of when we use this. If we were to come across the square root of a negative number, so the square root of -3, we could rewrite this as the square root of -1 times 3. The square root of -1 times the square root of -3, which is I, because the square root of -1 is I, and we can't simplify the square root of 3. If we have I times the square root of 5 squared, well, squared simply means we have two of them. So if we take I times I, we get I squared. The square root of 5 times the square root of 5 is the square root of 25. I squared is -1, and 25 is 5. So that would simplify to -5. And so now this is when we're going to use it, and I'm only doing one example, and if you need me to do more of these examples from your homework in class, I'll be glad to do that. So again, just like yesterday's assignment, we first need to get this x squared by itself, so we have to subtract 18, and then we're going to divide by 2, and we get x squared equals -45. To get to x, we undo that by square rooting both sides. So we get x equals, and we're solving an equation, so it's plus or minus the square root of -45. And we can break -45 up into -1 times 9 times 5. The square root of -1 is I. The square root of 9 is 3. and then we still have the square root of 5. Writing this in what we're going to call standard form, in that respect you're going to treat the I like you would treat a variable as far as how you would write it. So plus or minus 3I square root of 5. The sum and difference of complex numbers, and again this is just to expose you to some of the properties of complex numbers, but you're simply going to add the real parts or subtract the real parts, and you're going to add or subtract the imaginary parts. So in the first example, 12 plus a negative 8 is 4, and then negative 11I plus 3I, again you're somewhat treating the I as a variable. So we get negative 8I, so 4 minus 8I, and this is written, of course, in the form of A plus BI. In the next one, we need to remember to distribute that negative first, so it's actually minus 24 and plus 9I. Combining the real parts, I get negative 9, and then my negative 9I and positive 9I cancel, and so I'm left with just that negative 9. Again, in the third example, we need to distribute the negative, so minus 13 and a minus 4I. Combining the real parts and the imaginary parts, I get 22 minus 3I. This next example is an example of when imaginary units are used in circuit components, involve resistors, inductors, and capacitors. And again, this is just to expose you to when this is used in the real world. So we're going to find the impedance of a circuit. And so whenever you see, I'm just going to call it a zigzag, it's going to be a positive real number. Every time you see the coil, this is a positive imaginary unit. And anytime you see this symbol, it's a negative imaginary unit. So if we look at this first example, I have that coil. That means it's a positive imaginary unit, and there's a 3 in front of it, so it's 3I. That zigzag means it's a positive number, and there's a 5 in front of it, so plus 5. And then that symbol means a negative imaginary unit, so minus 4I. Combining my like terms, like parts, I get 5 minus 1I, which we can then just write as 5 minus I if you want. Looking at this example, so this symbol means a negative imaginary unit, so negative 7I, and then we have plus 12 and a plus a 9I. Combining my real part is a 12 plus 2I would be my impedance of that circuit. Writing each expression as a complex number in standard form. So the first thing we need to do is the same thing you would do if you had a variable. You're going to distribute. So negative 5I plus 8. We can multiply a real and imaginary part, we just can't add them. So this is negative 40I plus 45I squared. But remember, I squared is the same as negative 1. So we can replace that I squared with negative 1. We get negative 40I minus 45, but we need to write this in the standard form, which is the real part and the imaginary part, so negative 45 minus 40I. This next example, we need to multiply everything in the first parentheses by everything in the last parentheses, exactly the same as if there was a variable in there. So negative 8 times 4 is negative 32, plus 56I, negative times a negative, plus 8I, minus 14I squared. Combining my imaginary parts, the 56I and the 8I, and remembering that I squared is negative 1, negative 14 times negative 1 is a positive 14, and now combining my real parts, I get negative 18 plus 64I. Complex conjugates. In the same way that you couldn't have a radical in the denominator in the last section, and you had to multiply by the conjugate, so a plus b squared of b and a minus the square root of b are conjugates. Keep in mind that I is not a variable, it's the square root of negative 1, so you can't have an I in the denominator. So complex conjugates are a plus bi and a minus bi. And similarly, we have a difference of perfect squares, so when we multiply these out, we'll see that first of all those middle terms with the i's cancel, and then we need to remember that I squared is negative 1, so negative 1 times a negative b squared, leaves me with a plus bi. There's no I, and therefore there's no square root. So now let's go ahead and rationalize the denominator. The complex conjugate of 5 minus I is going to be 5 plus I. And so again, by multiplying by 5 plus I over 5 plus I, we're actually multiplying by 1, so we're not changing the value of our fraction. We're going to FOIL out the numerator, and when we do that, we get 15 plus 3i plus 20i plus 4i squared over, FOILing out the denominator, I get 25 plus 5i minus 5i minus I squared. Combining the real parts on the numerator and changing the I squared into negative 1, we get 15 plus 23i, and then again, that I squared is negative 1, so instead of being plus 4, it's going to be a minus 4. And then on the denominator, my plus 5i and minus 5i cancel, and that minus I squared becomes minus a negative 1, so I actually get 25 plus 1 on the denominator. Combining my like terms on the numerator, and then writing it as a real and imaginary part, I need to break this apart so I have my a plus bi. Plotting complex numbers. Well, we normally have a coordinate plane where we have our real axis, but instead of our x-axis is going to be our real axis, and our y-axis is going to be our imaginary axis. So 4 plus 2i means we're going to move 4 on the real axis and 2 up on the imaginary axis. So the I simply tells us that that's the imaginary axis. Negative 1 plus 3i, so we go back 1 on the real and up 3. So we're plotting these exactly the same way we would plot them on an xy coordinate plane. And again, in fact, it's listed in the xy orders, a plus the real part plus the imaginary part. The absolute value of a complex number. Well, if you remember that the absolute value simply means a distance, then you can see a little bit easier that this comes from the Pythagorean theorem. If we look again at the imaginary and the real axis, and we want to find the distance that the z is, well, that's the hypotenuse. So z squared equals a squared plus b squared. Well, if we take the square root of z squared, and we have to take the square root of the other side. And so we're going to have the absolute value because we're dealing with a distance, so we can't have a negative value. So that's the only reason that we're dealing with the absolute value, is the square root of a squared plus b squared. Now, a question I have for you, I want you to remind me about a question about this to see if what you will do given this kind of situation. If I have the square root of 9 plus 16, what is that equal to? Can you take the square root of 9 and the square root of 16 to get your answer? Alright, so let's find the absolute value. If we think about how these are graphed, if we go over 5 on the real axis and down 12 on the imaginary axis, then we could draw a triangle. We're trying to find this distance. So we have our real distance and our imaginary distance. So 5 squared plus, we're going down, so negative 12 squared equals our z squared. 5 squared is 25, negative 12 squared is 144, and that equals z squared. So z squared equals 169. Taking the square root, I have that z equals 13. And again, keeping in mind that we're dealing with a distance, we're only going to deal with the positive square root, so just the positive 13. The absolute value of 17i, well, that's up 17 units on the y-axis. And after we go through this, you'll see we go 0 squared plus 17 squared. So of course that distance is 17 units. That just intuitively should make some sense. Alright, so that is basically your introduction to imaginary numbers and the complex number. Remember to go back and do the notes check. And if you need me to do another example regarding solving equations, taking square roots and getting negative numbers, please make sure you ask me to do that, and I'll be glad to. We'll see you tomorrow.